Now let's see the laser applications. The laser beam has high power density, excellent directionality, and monochromaticity. The laser beam's excellent directionality allows us to concentrate all of its energy on a very small area. These laser beam properties are used in material processing and medical applications. The high monochromaticity of laser light, on the other hand, is utilized to send electrical signals modulated with laser light to distant locations via optical fibers. Lasers are used to cut, weld, drill, perforate, and heat treatment a wide range of materials. Since this laser beam can be concentrated on a very small area, materials are heated very locally. As a result, surface treatments are rarely required following laser processing. Welding different materials together is a difficult task. However, we can execute a clear welding job of two different materials without any welding flux by using a laser beam. Using a laser beam, for example, it is possible to weld plastic materials, which is problematic due to the difficulty in focusing the heat on a fine welding area. In semiconductor processing, micro-sized holes must be drilled and fine areas must be welded. These tasks can be completed with a laser without contacting other heat-sensitive regions. In material processing, high-power CO2 and Nd:YAG lasers are commonly utilized. This slide shows some examples of laser application. This is laser cutter. Using this laser cutter, we can make very small hole in the semiconductor material, or we can write some letters, very small sized letters on the semiconductor material, and we can also make this kind of very complicated structure using a laser cutter. It's also very complicated structure. And we can also use laser in laser printer and the laser pointer. The laser beam is used as a surgical knife in a variety of medical fields, including surgery, ophthalmology, and dermatology. A laser beam can cut a very fine region with high accuracy. Due to the numbing of blood vessels, bleeding can be significantly reduced when a laser beam is used as a surgical knife. The CO2 laser beam is utilized to vaporize malign tissues since water molecules absorb it well. Green light with a wavelength of 488 nanometer is emitted by the argon ion laser. Since red blood cells absorb this light well, it can be utilized to fuse the cleaved retina. It's difficult to get rid of port wine specks that have spread over a large area of skin. Here, we can bleach the speck region back to skin color by shining an argon ion laser beam on it uniformly. So can also use the surgical knife with the laser, and we can also get rid of the some stunk in the vein, and to flow the blood through the vein. This shows applications of lasers in medical area. X-ray laser, argon laser fluoride, and krypton fluoride. These lasers output this ultraviolet, and these lasers are used for cutting, incising, selective correlation, and also these lasers are used for LASIK. Argon ion laser has a wavelength of the 480 nanometer, which is blue color, and this argon ion laser is used for photo correlation, welding, evaporation, and also welding of retina, cutting laser or cartilage, and tattoo removal. Dye laser, we can also use dye laser for activation tumors, and selective correlation. And the dye laser we use is the wavelength is 631 and the red color. And Nd:YAG laser is ultra red vision. And this Nd:YAG laser is also used for photocorrelation and vaporization and evaporation. CO2 laser is also infrared laser, and this CO2 laser is widely used in the medical area for vaporization, incision, and most widely used in medical applications. Loop laser its wavelength is red color, 694.3 nanometer, and this loop laser is used for the treatment of carious tooth and tartar removal, and this loop laser is widely used for dental applications. For data processing and communication, a laser is also used. The communication carriers bandwidth delta F determine the communication channel's capabilities. The monochromaticity of laser light, delta F over Fc, the center frequency, is relatively low, but bandwidth delta F can be enormous due to the high center frequency Fc on the order of 10 to the 14 Hz. As a result, compared to radio system operating at a significantly lower center frequency on the order of 10 to the 6 Hz, the capacity of the communication channel can be greatly improved by using an optical communication system with a laser as a communication carrier and an optical fiber as the transmitter. Optical fiber cables, which are roughly the size of our finger, transmit about 50,000 telephone messages at the same time. Furthermore, the optical fiber telecommunication system has no crosstalk. In addition to communications, lasers are used for information processing, such as the laser printer, hologram, optical data storage, and so on. The combination of space and laser technology enables the laser remote sensing. Dust particles carried along by the wind scatter the laser beam produced by a high-power laser on the satellite. The Doppler frequency shift and the refracted light can be used to determine the wind speed and direction. Pollution is detected, harmful particle concentrations are identified, and specific atmospheric gases are measured using the same technique all over the world. Now let's see the optical fiber. In telecommunications, medical, and military applications, optical fiber is used to convey light signals. Optical fibers are formed by extracting molten glass in the shape of stars. Total internal refraction is the fundamental principle of sending light signals across an optical fiber. Both reflection and refraction occur when light crosses a boundary between two different media. The ratio of reflection to refraction is determined by medium's properties. If light travels from the air to the glass, for example, the majority of the light passes through the glass. If light strikes a flat metal surface, however, the majority of the light is reflected. If light travels from a dense to a less dense material, total internal reflection occurs. As shown in the figure below, this figure, light passes from a dense material with an index of refraction N1 to a less dense medium with an index of refraction N2. So this material is denser than this material. When light travels from dense to less dense materials, total internal reflection occurs. In the case of total internal reflection, the entire light signal can be transferred over great distances without losing any of its energy. The law of refraction links the incident and refraction angles, which is written as Schneer's law, which is described by this equation. The incident and the refraction angles are denoted by theta 1 and theta 2, respectively. If the angle of incidence is small, some light is passed to the N2 medium. So the incident angle is small, then some light is passed through to the N2 media, and some light also reflected back to the N2 medium. The angle of refraction, however, becomes 90 degrees at a specific angle of incidence. This is called the critical angle. That is, the refracted light passes through the boundary surface and is not transmitted to the N2 medium in this situation. So this situation shows the critical angle case. If the incident angle is critical angle, then there's no transmitted to the N2 horizon. Instead, the light is passing through the boundary between two medium. Okay. So the critical angle of incidence at which total interrefraction occurs. So this condition, the instant light is completely refracted back to the N2 medium at angles of instance larger than this critical angle. So the instant angle is larger than this critical angle, then all light is reflected back to the N1 medium. We can get the critical angle by putting theta 2 equal 90 degrees. So the critical angle is given by this equation. If you see this equation, only for N2 over N1 less than 1 is valid. Okay, so otherwise the sine arc value is this N2 over N1 can be larger than 1. So in that case, N2 is less than N1. So in that case, it means that the light is going from dense to less dense, then total refraction is possible. Otherwise, total refraction is not possible. This means that total interrefraction can only occur when light is transmitted from a denser to a less dense material. Since light is not transmitted to the outside when total refraction occurs, the light energy, the light signal, is not wasted. As a result, if the light signal is transmitted across the optical fiber using total interrefraction, it can be sent to far locations without wasting any energy. The light passes through the material border, this material border, if the instant angle of the light to the boundary is equal to critical angle. The light is completely refracted back to the instant medium when the instant angle is greater than this critical angle. To satisfy the requirement for total internal refraction, the optical fiber surface is coated with a substance that has a lower index of refraction than the optical fiber. Cladding is the term for this process. The optical fiber glass has a refractive index of roughly 1.5. The cladding of materials with a refractive index of N2 on the surface of the optical fiber with a refractive index of N1 is shown in the figure below. So this optical fiber, and on the surface of optical fiber, cladding material is coated, N2 material is coated. The critical angle requirement is satisfied by the instant light indicated by a red light in the figure. We get the relationship, this relationship, if we apply the refraction law to the interface surface 1. So this surface, if we apply the refraction law, then this is air, so N refractive index is 1, so sin theta m, and this N1 material, so N1 sin theta m prime, this angle. The refraction law on the boundary surface 2 here, on the other hand, gives the relationship, this relationship by Snell's law. The refractive index of this material is N1, Incident angle is theta c, and the index material of this material is N2, and refractive angle is 90 degrees. It's 90 degrees. And also we can have the angle relationship. This triangle, this S angle is 90 degrees. So sum of theta C and theta M prime should be in 90 degrees. So using these two relationship above, this one and this one, we can calculate the critical angle as follows. This equation. So the angle, incident angle for internal refraction is given by this equation. So dependent on the refractive indexes of two materials. The critical angle is the maximum incident angle of light on the optical fiber's cross section for total refraction. As a result, we must send the light to the optical fiber's cross section at the less than above angle, this angle, to achieve total refraction. The critical angle for total refraction is calculated as 14 degrees if a material having refractive index of 1.48 is cladded on the surface of an optical fiber with a refractive index of 1.5. So we can add this value here, N1 N2. We can get theta M as 14 degrees. Okay. As a result, light instant at any point on the cross section of the optical fiber with a cone angle less than 14 degrees will be totally refracted on the optical fiber's side surface. So this is optical fiber surface, and the angle. So this 14 degree and this also 14 degree. So corner of this angle. So if we send the light from inside of this cone, then light will be totally refracted from the surface of the optical fiber. As a result, the light signal will not lose any of its characteristics and will be transmitted over long distance via total refractions. Now let's see optical communication. Carl believed that the optical fiber's impurities lower the signal's intensity as it travels through the fiber. He noticed in 1969 that using high purity optical fiber only results in 4 dB reduction in light signal strength for each kilometer of transmission. This corresponds to the signal intensity dropping to 60% of its initial level during a 1 kilometer transmission. This demonstrated the possibility of optical signal transmission. The technique has been improved, and optical communication is commonly utilized today. This figure shows the schematic diagram of the optical communication. The digital pulse signal is generated from the analog signal and sent through the optical cable. So digital signal is directly sent to here, but if the signal is analog, then this analog signal is converted into the digital pulse signal using a digital converter. And this digital pulse signal is transmitted through the optical fiber, and these optical signals received by a photodetector and amplified, and then this signal is converted into analog signal by decoder to the phone or display. This signal is picked up and amplified in order to produce the original signal, which can then be heard or seen with the appropriate equipment. In the graph below, the optical signal's dissipation rate per kilometer is shown as a function of wavelength of the transmission ultraviolet light. So this y-axis is transmission loss, and the x-axis is wavelength of the ultraviolet light. Because of its very high rate of dissipation, visible light is inappropriate for optical communication. Instead, optical communication makes use of ultraviolet light. As a wavelength of 1550 nanometer, the minimum dissipation rate of 0.28 dB per kilometer is observed. So around here. So the telecom bands for each wavelength region are shown in the figure: S-band, O-band, E-band, S-band, C-band, and E-band. This calls telecom bands. The LED is utilized for transmitting data over small distance and not at high speed, since in this situation, little power is allocated for data transmission. On the other hand, because lasers have a high power and narrow frequency bandwidth, we use them for long distance or fast data transmission. The other benefit is that optical fiber's diameter and the laser line widths are comparable. Three different types of semiconductor lasers are now utilized in optical communication. They are VCSEL, DFB, and FB red lasers. We will discuss these lasers further below. As was already explained, the ultra-red semiconductor laser is required for optical communication. In the semiconductor laser for the resonator, the multilayer thin films are coated on the two ends of the semiconductor to form the fabric parrot laser. The fabric parrot cavity structure is thus made up of 2 mirrors at the ends of the semiconductor. These types of semiconductor lasers have narrow frequency bandwidth and high laser output. Therefore, long-distance communication uses these lasers. The VCSEL, vertical cavity surface emitting laser, we already discussed these lasers, has a different structure from an H emitting laser and emits light vertically. So this is a peripheral H emitter laser, and this is VCSEL. In the H emitter laser, the laser output is coming from the edge, and VCSEL laser output is coming from the surface of the laser this way. The edge emitting laser is used to form a peripheral laser. If we utilize VCSEL laser for optical communication, the optical communication device can be tested before it is assembled, since the laser light of the VCSEL is emitted from the front surface of the chip. Okay. The optical communication device, however, can be checked once it has been put together if we utilize the H emitting laser. As a result, it is possible to significantly reduce the cost of producing the optical communication device if we use the VCSEL laser. On the 3-inch gallium arsenide substrate, tens of thousands of VCSEL lasers can be produced simultaneously. So this is possible because laser light emits vertically. The multilayer thin films are coated at the two ends of the active layer to form the peripheral resonator. So multilayer films are coated here and the other ends, and so these two multilayer film forms the peripheral resonator. So we call this kind of laser peripheral edge emitter laser. Instead of the H direction, like an H emitting laser, the VCSEL produces laser light vertically from the surface of the laser. The grating is made at either the top or bottom of the active layer to form the DFB, distributed feedback laser. The grating will then only let a specific wavelength of light to reflect back to the active layer. Because of this, the laser output only amplifies light at that specific wavelength. Distributed feedback is why the name DFB comes. Despite costing more than peripheral laser, this DFB laser is suitable for long-distance optical communication. The FB laser emits a mixture of various light modes. On the other hand, when the DFB is utilized, we may attain the single mode of light. However, in this case, the light's output power is not quite as strong as FB lasers. The DFB and DBR lasers differ depending on whether the grating is produced within or outside the active layer. So we can fabricate the grating here, then we can amplify the light at the specific wavelengths, and DFB we formulate the grating here, and DBL laser, the grating is outside of the active layer, and the DFB grating is inside of the active layer. There is difference. So here, DFB and DBR lasers differ depending on whether the grating is produced within. So this is within the active region, and DBR, the outside the active layer. There is the difference. The FB laser's output is shown in the left figure, this figure. The standing waves that formed in the cavity are mixed together in this output, resulting in various combinations of wavelengths. You can see here the laser output consists of various light wavelengths. The output of the VCSEL depicted in the right figure, this figure. This output is similar as a single mode wave. So the single mode wave. A specific wavelengths of light among various light modes of the FE laser is amplified by the FE laser. So in the FE laser, specific wavelengths is amplified to give the output. So there is a very pure wavelength. As a result, the DFB laser's output is similar to VCSL's output shown in the right figure. So this is the output of the VCSEL laser, and if you use DFB laser, the output is very similar to that shown in this figure, which is the output of the VCSEL. The DFB laser's amplified wavelength is expressed by this equation. Here, lambda and n stands for respectively the spacing between consecutive grating rulings and grating material's effective refractive index. So lambda, so grating is given by this figure. Then lambda is the spacing between consecutive grating rulings. So lambda is distance between two grating rulings. So this is lambda. Okay. So we can control the output wavelength of the laser by adjusting this lambda. Lambda is spacing between consecutive grating rulings. This slide shows some examples of laser application. This is LASIK. LASIK means the laser associated stromal in situ keratovilicious. This word stands for corneal reshaping. So LASIK is used to correct myopic eye. An eye is consists of two lenses. One is cornea, this is cornea. The other is the crystalline lens, In the LASIK, the cornea is slightly flattened by using laser. So this part is removed, and then cornea is flattened. Then the focal length of the eye lenses is increased to form the image on the retina. So in this way, we can correct the myopic eye. So LASIK technique is widely used for correct the myopic eye. And that is this figure is the portable ND arc laser. And this picture shows the laser used as a surgical knife for laser surgery. And this figure shows the tooth decay treatment using ruby laser.